Okay. So, are there any questions on what I did last time? Good. Now, last time I completed essentially my review of the standard model, but there is one thing which if I don't do, I think it might dog us in the future. So I just want to do that hopefully in 10 minutes and then I'll start on the supersymmetric case. And this has to do with discrete symmetries of the standard model. And specifically CP and T. And this is a little bit subtle, so it's worth doing once. So the first question, the question of concern to us is how do CP and T act? Okay, charge conjugation, parity and time reversal. As you probably know, we only have to answer two of these questions because exact CP-T invariance is a necessary requirement for all four-dimensional quantum field theories. So whatever we know about C and P will tell us the answer for T. For example, if C is violated and P is, I'll tell you the answers. We'll find that C is violated, P is violated, but CP is conserved and therefore T is conserved. Okay, in some classes, in some approximation to the standard model. And in some other approximation, when we are more careful, we'll see that CP is also violated. In that case, T is also violated. So T will never be examining separately. Okay. Now we want to understand this physically and not just through some equations. So the question is, what is the action of C and P on a fermion of the standard model? Yes, what? It's orbital. Now how do you know it's being captured?
Because last time, if I talk from here...
Really? I thought it's a directional line.
No, it's a line.
Okay, well, too bad. I think that work has to be done. We can't stop it. Okay, so the question is how do these things act on the fermions? So as usual, it's the fermions which are crucial. And we could ask, for example, that C, starting with the left-handed electron, what does it do? And P, starting with the left-handed electron, what does it do? So does anyone want to guess the answer? What does C do to a left-handed electron? Left-handed positron, thank you. So this is E dagger L, which also happens to be E right dagger. Okay, we've been through this. On the other hand, under parity, EL goes to ER. Okay. Now it's immediately apparent whether C and P are preserved by the standard model. Okay. That would be true if the couplings of EL are the same as those of E dagger L and the couplings of EL are the same as the couplings of ER. So is that the case or not? It's not the case because SU2 has different quantum numbers, so right at the level of quantum numbers, forget about the actual couplings, even the allowed couplings, even the in principle allowed couplings, just by choosing the representation content, this is in a doublet, this is in a singlet, therefore its dagger is also in a singlet. So C maps something in a doublet to something in a singlet, so no chance of the symmetry being there. Okay. Moreover, we can see who to blame. It's the SU2 symmetry which is going to violate. It's the SU2 sector of the theory which is going to violate C. For example, as far as the SU3 sector, the strongly coupled sector or the strong interaction sector, E left and E right are both singlets of SU3, so that doesn't matter. But this one is going to violate it as much as it possibly can. It's a maximal violation. Likewise, this is in a doublet and this is in a singlet. Okay, so this is also going to be violated. So both violated. Okay, the situation is somewhat better for C times P because what C times P does is to actually transform this thing first by sending it to E right by P if you like, and then C will dagger this thing and sorry?
I just said it would be EL dagger.
EL dagger. EL dagger, yes, that's correct. Thank you. So CP sends EL to EL dagger. Okay, and what that does is that it sends the doublet to the dagger of itself, which is also a doublet. Okay, and so there's a much better chance for that to be conserved. And in fact, it's conserved by terms like -1 for f squared and I chi. These kind of terms. These are basically kinetic terms for the gauge fields, which include interactions because these are non-abelian gauge fields, as well as kinetic terms for the fermions, which also include interactions because of the covariant derivative. So this whole bunch of things, which is dictated entirely by the gauge symmetry, is going to preserve CP. Now, the Higgs is not going to do anything interesting. It's really going to be the Yukawa couplings which have a chance of violating CP. So let's look at the Yukawa couplings. And let's focus on some particular one. Okay, instead of focusing on a particular one, perhaps we can just remember what we did last time. Last time we had a bunch of Yukawa couplings which were like minus F, D, we call it star, I, J, Q, left, I, phi, D, right, J, etc. These are the Yukawa couplings. Okay. Now, it's quite easy to check that CP will take the operator Q, L, I, phi, D, R, J to itself complex conjugate. Okay. Now, what's the actual interaction? It's really this plus its own complex conjugate because the Lagrangian has to be real. Lagrangian can't be complex. Okay. But when we complex conjugate this term, then of course we complex conjugate the operator, and this coefficient, if it's complex, will also be complex conjugated. Okay. Now there's no point saying we'll restrict it to be real. Okay. We want to look at the most general possible couplings. Okay. Then if any of them is zero, then we need an explanation physically why it's zero. It should be protected by some symmetry or something. Okay. The important thing here is that nothing stops this being complex. Certainly not reality of the Lagrangian, because after all we are going to add this term. So whatever thing is complex here, there will be a complex conjugate term. Okay. But CP only conjugates the operator. Therefore, naively, if F star D is complex, we have CP violation. Okay. Now this naive statement is wrong for the following reason. This assumes that we make CP transformations in the most naive way on these operators, and we have already seen in the last lecture that if I make unitary transformations on these left and right things, then the coefficients F get conjugated by those unitary transformations. Okay, so they can be changed. So there's a basis dependence to this statement. In other words, it's true that if F is complex, then in this basis CP is violated. Okay? But we can't conclude that physically CP is violated. We can conclude that maybe we have simply defined C and P wrong. Okay? Because the definition of C and P in a given basis is this, but if I make a unitary transformation on the fermions, then the definition of C and P will change. Okay? So the correct way to ask the question is, can I, by making suitable unitary transformations on the left and right fermions, make CP conserved? Okay, in that case, the physical theory will conserve CP. Okay, this is an important point for you to realize that a symmetry is some realization of the abstract operator CP on the theory, and if the realization you think of isn't a symmetry, that doesn't mean the symmetry doesn't act on the theory. Okay? Because the physical consequences of the symmetry will be visible in amplitudes. Okay? And those consequences will derive from the action of the symmetry in whatever way it actually acts. Which if you are not aware of it, you wouldn't realize that the amplitudes have that property. Okay. So in other words, to look for CP symmetry of a theory, it's not enough to say I'm going to just conjugate these fields in this way and see whether CP is satisfied, and if it's not, then it's violated. What you have to do is ask for all ways of defining C and P on the theory, and then ask whether it is preserved or violated. Okay. And all ways amounts to all changes of basis, and so you can see what I am driving at. If by a suitable change of basis I can make these real, then CP is conserved. Okay. That's really the one line statement. If by a suitable change of basis F then CP is conserved. Yes.
In the Lagrangian we have that term plus its complex conjugate.
Yes.
So CP is integrated in the Lagrangian.
Yes.
So is it CP-violating?
No. See, in the Lagrangian we have this times this operator plus the conjugate of this times the conjugate of this operator. Under CP we get this times the conjugate of this operator plus the conjugate of this times this operator. Not the same. Okay. So the question we want to ask is whether CP can be made to be conserved. That is, whether we can make all the F's. There are many F's, remember. There is one F for Q left with D right. There is another F for Q left with U right. Okay, actually those are the only two F's in the quark sector. We'll come to the leptons later. Okay, because this DRJ is all the three generations of down-type quarks, and URJ are the three generations of up-type quarks. So those are all the F's, the FD and the FU. So actually the question then is whether we can make all of those here. Okay. Now actually that question just collapses into the question of whether we can make the CKM matrix real. So this in turn depends on whether the CKM matrix, which is defined to be Vij equals U. So this is the unitary transformation acting on the up type left-handed work dagger. Acting on the down type left-handed work can be made real. So I'm not going to show in detail. One direction is obvious. If it can't be made real, then it's pretty clear that these F's cannot be made real. Okay? But if it can be made real by some change of basis, then actually the F's can be made real. Okay? So I'm just going to show you what we need to do to ascertain that. So for that, you know that I and J go from 1 to 3 because we have 3 generations, but we'll take a 2-generation model first. And instead of bothering to write out V in terms of all these matrices, we'll just make the most general parameterization of a 2x2 unitary matrix. I hope it's clear from this that V is unitary. V is U1 dagger U2 for 2 unitary matrices. So V dagger is U2 dagger U1. You multiply it all out to get 1. So V is unitary, and there are many ways to parameterize a unitary matrix, and this is not the one that would obviously come to mind, but it's one that's very convenient for this problem. So we parameterize it in terms of 4 angles, theta c and alpha, beta, gamma. And what you need to check is that this is the most general 2x2 unitary matrix. Hardly anything to check because the unitary matrix n by n has n squared real independent components, and this matrix has n squared real independent components. So basically you are done. So So this is one way to parameterize it. And now, in this 2 by 2 basis, we are allowed to make further. So the question is now, how do we ask whether we can remove all the complex parts of this matrix? And you see that amounts to removing alpha, beta and gamma, but leaving theta. Okay. Physically also, this is very appealing because theta being a single real angle will actually give me the mixing between the first and second generation. We already saw that mixing is just a rotation between two things, and it can always be brought to a rotation of the lower components. Okay. So between the down and the strange quark, there will be mixing parameterized by theta c. If there is anything else which can't be removed, then it's a CP-violating phase. Okay. And it's not to say that there's a lot of trouble if that happens, it just means the theory is CP-violating and we need to explore from experiment whether that can be confirmed and it agrees with the prediction. Okay, it's a constraint on the model. But in this case, what we find is that we can remove the phases by the following process. We put together all the 4 quarks, U1 left, D1 left. These are the left-handed quarks of the first generation, and then U2 left and D2 left, which are actually just names for charm and strange left. And we allow each of them to transform by an independent phase. And the question is, how does this affect the CKM matrix? Okay, so this affects the CKM matrix by multiplying it on both sides by, well, this changes Bij to a matrix, then V and another matrix, and the left side is e to the I delta 1. To the I delta 3. That's because those come from U1, U2, okay, and U1, U2 are the ones which are affected by the matrix capital U of U lefts, okay. D1, D2 are the ones which are rotated by the matrix capital U of D rights, okay. So the phase on U1, U2 comes on the left, and the phase on the other two comes on the right, and I guess one of them comes with the minus sign, but that hardly matters. These are all arbitrary phases. Okay, so here's V, and here's what happens to it after we make this general phase rotation. And the question is, what does it take V into? So simple multiplication, and we find the answer to be V goes to the matrix readable? Okay. Now we notice two things. One is that if all the deltas are equal, then there is no effect at all. Okay. That's not surprising because that amounts to a uniform phase for all the quarks, but a uniform phase for all the quarks can be absorbed into that unitary matrix. Okay, because the unitary matrix was the one that was acting on U1, U2 and acting on D1, D2. Okay. So it shouldn't do anything, and in fact it doesn't do anything. However, if we choose one of these four to be 0, So it's convenient to choose delta. Because all four of them together don't do anything, it means we might as well fix one of them to be 0 and then the other three will do something. And what the other three do is to send alpha to alpha minus delta 2, beta to beta minus delta 4 and gamma to gamma minus delta 3. You can just see that by inspection of this. Actually, by comparing the matrix I just rubbed out with that, you see that wherever you have alpha, now you have alpha minus delta 2 and so on. One of them is plus, that's correct. Gamma goes to gamma plus. Thank you. That's exactly right. Okay? And so I hope this convinces you that we can therefore remove all of them, alpha, beta, gamma. Okay? And the surviving mixing matrix is just cos theta c sin theta c minus sin theta c cos theta c, with theta c being the Kabiba angle. That's exactly what you expect. It's a single real U1 rotation between the first and second generation, and that's all you would expect it to be. Okay. And this thing surviving shows that there is mixing if theta c is measured to be non-zero, which it is, but at the same time there is no CP violation. Now we've done this for the 2 by 2 case, and we can easily repeat the same thing for 3 by 3 without going through all the mechanics. It's just a matter of counting numbers. So this is actually Kobayashi and Masukawa's important contribution. They in fact historically proposed that we should add a third generation before it had been discovered, on the grounds that once we have a third generation, we won't be able to remove all the angles and there will be CP violation. Okay. The third generation worked out on various other grounds, of course, and of course it's experimentally observed. But this was a kind of reason that they had in mind. So let's show that that is the case. So with the 3 by 3 generations, V, the unitary 3 by 3 matrix, has 9 real parameters. Okay. Now, out of these, 3 will be in SO3, and those will be the 3 analogues of the Kabiba angle. There will be the 3 parameter SO3 rotation between the down quark, the strange quark, and the bottom quark, the lower components of the 3 generations. If they are all going to mix, then of course there will be a 3 by 3 matrix that does that mixing, but it will be a real SO3 matrix. It's not going to be a complex or unitary matrix, it will just be a real matrix in SO3 parameterized by 3 angles, just as you expect. Okay, so that means that the remaining 6 are going to be phases. Maybe that's not completely obvious, but it's true that the remaining 6 parameters of this matrix are phases. So our job will be to remove 6 phases if we want to have CP in the CP invariance. Okay, so can we remove 6 phases? And the answer is clear. We have 6 different quarks on which to act with phases. Okay, so but all 6 being transformed by the same phase will do nothing, just as it did in this case. Therefore, there are only 5 independent phases. So we have only 5 independent phases. On 6 left quarks. Therefore, one phase remains. And therefore, we conclude that the 3 by 3 mixing matrix has one CP-violating phase. So this is one origin of CP violation in the standard model. Okay. Therefore, the standard model in principle does not conserve CP. Now, an interesting fact is that the standard model until a few years ago didn't have a right-handed neutrino, because it was thought that neutrinos are massless, and therefore there was no need for a right-handed neutrino in the theory at all. And because of that, if you repeat the same procedure in the lepton sector, you find that actually there is no mixing at all. Okay, so there is nothing to mix and there is no mixing, and so there is no origin for CP violation from the lepton sector, only from the quark sector. But now we do have right-handed neutrinos, and we can have CP violation also from that sector. In keeping with what I am doing up to now, I am not discussing neutrinos, and therefore I won't go into the issue of CP violation in the electron sector. Besides which, it will be of interest to us only in as much as it comes out in the MSSM, and we haven't got there yet. So I am actually now going to stop with this. I just wanted to make this point so that you realize that CP is generically violated in the weak interactions. There is also a way by which CP can be violated in the strong interactions. Do people know this? Theta angle. Thank you. So there is a possibility of a theta term, which is theta times f dual. Although f dual is in principle a total derivative, it can have consequences, physical consequences, and they lead to CP violation, but at a strength typical of the strong interactions. That's called strong CP. But again, it's not something I need to discuss just now. Okay. So I'm going to close this discussion of the standard model and start talking about supersymmetry. Are there any questions? Now, when I originally planned this course, I was sort of under the impression that everybody taking it would know everything there was to know about supersymmetry in all possible dimensions from 2 to 10. But I think that's not true. And also, it turns out that 4-dimensional supersymmetry has somewhat unique practices in terms of notation, such as the 2-component notation and so on. So, and also, I was going through Wess and Bagger and DGR, the other textbooks yesterday, and I was really, honestly, not happy about the fact that they introduced supersymmetry by taking something like 10,000 equations and hitting you on the head with it. That's not, I think, how you should think about supersymmetry. So maybe I can add a little value to your perception of supersymmetry by telling it to you in my way of looking at it. And what I'll try to do in terms of equations is write only the few which give us the idea that what is happening geometrically. All the other equations can be derived. One of the things that Wess and Bagger really did was to write groups of 12 equations where 11 of them are just some fancy complex conjugates of the first one. And that, I think, doesn't help. I mean, it just something, it looks like something you have to memorize. So let's try to do it a little better. Okay, I shouldn't say better, just let's try to do it differently. Okay. So the way I would like to motivate it is that there are perfectly sensible Lagrangians, which we might write down for our own reasons, for example, while studying field theory, which have a remarkable symmetry in them. And this occurs even when we write down Lagrangians that are non-interacting. And here's the first example that I'll write for you. It's just a theory of one wild spinner, fermion, and a complex scalar. Okay, as you see that this is the free theory with just kinetic terms. But I can add also the mass terms. This is all as per the conventions I've already shown you. Okay, so here's the theory. Now this free Lagrangian is invariant under some transformations of the type phi and phi star get interchanged with psi and psi star. Now, interchange is not a very good word. What we really mean is that these are infinitesimally varied to acquire a component in the direction of these, and these are varied to acquire a component in the direction of these. Okay. If you examine the Lagrangian, it's obvious that it can't be invariant under actually an interchange of the two. For example, this is a second derivative kinetic term, this is a one derivative kinetic term, this is not possible for those to interchange. Okay, but what can happen is that there can be a Lie algebra Okay, some action which takes a given configuration and varies it slightly infinitesimally in that direction, and a configuration of this and varies it in this direction, and then we'll find that this is an invariance of the theory. So to write it quite precisely with all factors, the infinitesimal variation of phi is epsilon psi. Epsilon is a constant two-component spinner, and the variation of phi star is just the complex conjugate of this. So we needn't even have written that equation. The variation of psi is a little more complicated. Even before you get to it, in case you ever need to remember these things, you know that phi is a scalar field in 4 dimensions, so it has canonical dimension 1. Psi is a fermion field, so it has canonical dimension 3/2. So therefore epsilon must be formally assigned a dimension -1/2 to make sense of this equation. Once that is so, this is 3/2. There is going to be -1/2 from an epsilon on the right side, so the rest of it must have dimension 2. But it has to be linear in phi, therefore there has to be something else which makes the dimension up to 2. The two possibilities are a derivative operator or a mass. Okay, so we expect two terms, one of the form del phi and another of the term m phi. Okay, is that clear on very general grounds? This is how you can remember these things even without recourse to a textbook. Once you agree that you need del phi, then of course you need something like a sigma matrix to contract away the derivative index, because you only allow one derivative. Okay, but once you agree to have a sigma matrix, remember psi had an index downstairs, spinner index A. This has indices A, B dot. Therefore, you must contract it with a dotted spinner. So, with an epsilon dagger. Okay, so everything sort of follows. The only thing I can't derive from all this is the I or the minus, but those are easy. Again, if you are stuck on a desert island, just put arbitrary numbers and then try to see what satisfies what is actually a symmetry. So this is one term. The next term is going to have m, because we said other than derivative we can only have m. Okay, it's going to have phi star, as it turns out, and epsilon. So epsilon is easy to predict because this time psi has a lower spinner index. These have no spinner index, so this must be with the lower spinner index, undotted, so it's epsilon and not epsilon dagger. So the two terms, one has epsilon dagger, one has epsilon, and well, one has phi and the other has phi star. Actually, if you go through some kind of charge assignments, you'll be able to even convince yourself that this should be the case. Okay, basically what you'll have to do is think about how to associate charges with phi and psi, and then you'll be able to even see that phi star must occur here. And then there's the complex conjugate equation, which we actually do need. Delta psi dagger is minus I sigma bar mu del mu phi star epsilon minus m phi epsilon dagger. There's not much that could have happened in diagramming this equation except some signs. This one I think is absolutely straightforward, but here what happens is that sigma changes into a sigma bar, I changes to minus I, but then I think there's another minus sign from diagramming the sigma. So hopefully this all works. Moreover, remember that sigma bar naturally has two upper indices, first one dotted, second one undotted. So this is psi dagger upper A dot, this is upper A dot B, therefore this is lower B. Okay, so you have to check all those things. You should also be in the habit of putting in indices into equations back once in a while as a kind of challenge, like am I following this properly? If I'm following this properly, I should know how to put all indices in this. Good. So I claim this is an invariance of this Lagrangian, and I'm going to actually show you that it is so. Also partly to see what's the simplest way to do this. We'll probably never need this in the course, but if you've seen it once, that's pretty useful. So claim is that actually delta L under this is a total derivative, it's not zero. It's a total derivative. Okay, so let's prove it. Proof. First thing to note is that there is a dimensional parameter m in this action, and also there is a epsilon and an epsilon dagger appearing in the variations. Okay. Now if things are to cancel out, they must cancel out separately for epsilons and epsilon daggers. Okay. Moreover, they must cancel out separately for terms of different powers in M. So therefore, we'll do the proof in 3 stages. First, 0th order in M, and for epsilon variations only. This doesn't mean that we can make a variation involving epsilon without making a variation involving epsilon dagger, which is its complex conjugate. But it means that we can check the variation being 0 up to a total derivative by looking only at terms in epsilon, and then we can simply add the complex conjugate to that. That's a useful thing. So 0th order in M. So in that order, the variation of L is first of all epsilon del mu psi del mu phi star. This comes from taking this and varying only phi by this rule. Epsilon is constant, so we get this. We don't bother to vary phi star because it would give epsilon's dagger. Okay, so that's one term. And the other term comes from looking here and varying psi dagger by this term. Okay. If we vary psi in this, then we either get an epsilon dagger term which we don't want, or we get an M term which we also don't want. Okay, so therefore we have to vary psi dagger and keeping only this term. That means we have I psi sigma mu del mu, and then minus I sigma bar mu del mu phi star epsilon. Again, it's a good idea to keep track of where all the indices are going. This del mu phi star doesn't belong in here, it can be taken out. Psi, sigma mu, and epsilon, sigma bar mu and epsilon are all inside. These sigmas are between two spinors. Okay, you just have to look at it a bit. Okay. So the first term is, we just rewrite it. For the second term, I and minus I cancel each other out. Okay, and del mu acts only on del mu phi star. So it's plus del mu phi star psi sigma mu sigma bar mu epsilon. So far so good. Now I hope you can see what's going to happen. We are going to use the symmetry in mu and nu due to this del mu to symmetrize sigma mu with sigma bar mu, and that symmetrized product sigma mu sigma bar mu plus the opposite is eta mu. Okay. This plus its opposite is twice eta mu, but it's only this, so it's half of that thing, so it's eta mu precisely, and that means that we get epsilon. First term I'm rewriting as before, and the second term is del mu phi star times psi epsilon. Alright, and now we are through. This is d mu of epsilon psi times d mu phi star. That's the promised total resistance. That's only part 1 of the proof. It's 0th order in M. Now we have to do first order in M and second order in M. So part 2 of the proof is first order in M. So for first order in M, we need to do the following. We need to realize, I wrote out the supersymmetry transformations, so you have them somewhere. I guess I could put them here. We only need to know this. So we don't need to vary this term at all, because it's never going to give me a variation involving M. So now I can forget about this term. We need to vary this term by something which contains M and also epsilon, therefore we need to vary psi, therefore we need to vary the first term. Okay. Now there are two things here, so it's actually minus M psi and the variation of the second psi. Here you have to be a little bit careful, because one of these has an index up, the other has an index down. There are some dangerous minus signs. But it's always safe to vary the second one, because the second one in this case has the index down, which is also true of this. And here the second one has its index up, which is also true of this. So that's how it works. So we get minus m psi times the variation minus m phi star epsilon. Oops, no, wrong number. What was I trying to do?
First term.
So then I have to vary, sorry. I have to vary this term, and I have to keep this piece of it. Because there's already one m in front. There's already one m, I'm working to first order in m. So this doesn't give me anything in epsilon, this gives me something in epsilon and without an m, which is all I need. So therefore it is minus m psi dagger times minus I sigma bar mu del mu phi star epsilon. That this one, this, okay. Yeah, but then that m will multiply this m to give me 2m's. M squared. I'm still working to first order in m, and I'll have that as soon as I go to second order in m, which will be the last stage of the proof. Okay. So here is one term, which is correct. The other term, I need to vary the kinetic term, and within it, I need to vary the first piece psi by minus m phi star epsilon. Okay. If I vary psi dagger, then I would get epsilon dagger. It's all kind of common sense. So I times then minus m phi star epsilon, and then sigma mu del mu psi dagger. Okay. So things are not looking too bad. You see that we have a epsilon in both, we have a psi dagger in both, we have an m in both, we have an I in both. So hopefully everything is going to work out. So the first term is I m del mu phi star psi dagger sigma bar mu epsilon. So this is a good way to arrange terms. This is a spinor with a matrix in between, and these are just some things which have no spinor properties. And then the second term is minus I m phi star, and then epsilon sigma mu del mu psi dagger. And now the last thing I need to do is to reverse the order of one of them. So I'll take this one and I'll rewrite it as, so a spinor times sigma bar times another spinor is minus of this spinor times sigma times that spinor. That's an identity which you can prove. So it's minus I m del mu phi star epsilon dagger sigma mu. So the identity I've used is chi sigma mu bar theta equals minus theta sigma mu chi. Again, there are lots of things you'll have to remember while checking this. Sorry, something has to be like that. In each case, I think I'm daggering the. What have I done here? I've done something wrong. Okay. So, indeed, to put a dagger on one of them, that's the wrong place for the dagger. The dagger should be here on the right and here on the left. That's because sigma has first undotted and second dotted both down. This has first dotted and second undotted both down. Okay, so that's an identity. With that identity, I got a minus sign and this, and then I added to minus m phi star, and you can see how nicely it's all working out. This is equal to del mu of minus I m phi star epsilon sigma mu psi dagger. Right? Del mu can act on phi, then I get this term, or it can act on psi dagger, then I get this term. So that's it. So we've got all the terms, except now we have to do second order in M. For convenience of Blackboard space, I'm not going to do second order in M. In fact, I'm not going to do it at all. You can do it. So second order in M is left as an exercise. It's very simple, and it also doesn't add anything to the total derivative term. The reason is second order in M means I vary a term like this by a term like that. Nobody has any derivative in it. It's already a order M squared. So it can't give a total derivative term, so we'll find that they just add up to 0. Okay? So once we are through with that, we conclude that the total derivative, the conclusion is variation of the Lagrangian is equal to, this came from 0th order in M, this came from first order in M, so we'll add them together. So in one term you see the dimension and the vector index are coming from a derivative. In the other term the dimension is coming from M and the dimension is coming from M and the index is coming from a sigma. Because this has to be a vector, because del of L has to be d mu of J. Okay? And I suppose you know by Noether's theorem, so this thing should be the current. Okay. If there is an invariance, then this is a conserved current. And it's conserved by virtue of the equations of motion, which is easy to check because the term when del mu acts here, you get box of phi star, which is m times phi star. And when it acts here, you get del slash of psi dagger, which is m times psi dagger, and then those two terms will cancel. Sorry, box of phi star is m squared times phi star. So you can check that this current is conserved when you use the equations of motion. Okay. From this, you can generate from this J mu. Also, let's examine what is this current. It's called the super current because this transformation we've just been studying is supersymmetry. How many indices does it have? Well, we should take out epsilon, which is a spinner, which is the parameter of the transformation. Then psi contributes a spinner index, okay, a lower undotted index. Sigma mu psi dagger also has a lower undotted index after you contact this, as well as a vector index. So it's really J mu A. And there will be it will be added, we only did the epsilon terms, there will also be a corresponding J mu A dot. Okay, so it's a spinner, it's a vector spinner current for one thing, in the sense that it has both vector index and a spinner index. It's called the super current. And since this is supposed to be a very brief and practical review, I am not going to pursue this. But you know that if I take mu equals 0 and integrate in d3x, then I get the corresponding charge, and you can check that by canonical commutators, that charge reproduces the supersymmetry transformations that we started with closing the cycle. Okay. Now, this is great, except that it's only a statement about a very uninteresting free field theory. Okay, so what are we going to do with it? Well, if we really want to extend this symmetry to more general theories and interacting theories, then we need a sort of formalism in which the symmetry is manifest. Okay, and that formalism will be the superfield formalism that we'll come to in a moment. But even without going to that, I would like to offer you one more example just to show you that this phenomenon is not confined to just this Lagrangian. Here's another one. In this case, I have a free abelian gauge field whose kinetic term is that. and I have another spinner. And I can think of this as a Majorana spinner quite naturally. If you remember, my Majorana conventions had a 2, but then it also had a double-edged derivative. So up to a total derivative, this is the same as for a Majorana spinner, and it doesn't have a mass. Okay, so I've just taken a massless Majorana spinner. Actually, whether you call it Majorana or Weil doesn't matter in practice. Okay, it's a lambda and a lambda dagger. Of course, the Weil spinner also has its ion side. Now, this theory is massless because after all the gauge field is massless to preserve gauge invariance, and so we've chosen not to put a mass for this either, otherwise it's unlikely there would be any symmetry between them. So now the claim is, and this is a nice exercise for you because it's not very easy, it's easy but it's not very easy, is that under these transformations, lambda dagger CC of this action is invariant. Again, delta L is invariant up to a total derivative. So this is your exercise. So to give it a try. Notice a few things about this. One nice thing is that if you think of this from the point of view of gauge symmetry, this Lagrangian is gauge invariant, of course, because F mu nu is gauge invariant. This is just abelian gauge invariance. Okay. Now, in an abelian system, of course, the theory is free, and things that couple to it will have interactions with the gauge field only if they are charged, like in QED. But here we've purposely taken a neutral spinner, so it's also free. There's no covariant derivative, it's ordinary derivative. Okay? So actually this is completely neutral under gauge transformations. If you make this non-abelian, then this would turn into an adjoint field because the gauge field itself is naturally in the adjoint. And then we would turn this also into the adjoint representation, and then we would be able to have supersymmetry. Okay? But the abelian version of an adjoint representation is just trivial. Unlike the fundamental, whose abelian version has a charge, the adjoint abelian version is trivial. So in this case, it's just a free theory. But as far as gauge invariance is concerned, that means that gauge transformations don't act on lambda. For that property to be preserved by these things, we see that here the variation of lambda is itself gauge invariant. Okay. So that's a good thing, and you see that when I vary the gauge field, I need to have this index appear on the right side. So instead of epsilon lambda, which is the structure in this model, we have epsilon sigma mu lambda. Okay, but now since there is a sigma with one dotted and one undotted index, we must have an epsilon and a lambda dagger, not an epsilon and a lambda. You can predict the structure of this term was not epsilon sigma mu lambda because there is actually no such thing. Because of the sigma matrix having one dotted and one undotted index. Okay. Conversely, here this is an epsilon. This is the sigma mu nu matrix, which has what kind of indices? Yeah, both of the same kind, A and B. Let's say both undotted, and moreover one up and one down and one up, because it's made up by multiplying sigma with sigma bar. Okay, so it's actually sigma mu lower A upper B. This is lower B. This is lower A. Everything matches fine. Okay, so therefore lambda varies into an epsilon and lambda dagger independently varies into an epsilon dagger. So all this structure is fixed, and you can enjoy working out the invariants. Okay. Now let's get back to this one. Just to give it a name, this is called the free Wess Zumino model. That means that there will be an exacting version of this. And it's just a model involving one scale, spinner and one complex scale. Okay. Now, again, textbooks tend to hit you with a huge many line thing called the supersymmetry algebra. But algebra is nothing but taking a symmetry transformation and performing it twice in the two opposite orders and comparing what you get. So we can just do that and we find the algebra. It doesn't have to be postulated. That's why I like this model. It contains everything you need to know to guess what is the general structure of supersymmetry. So to find the algebra, here's a strategy that always works. Pick a field. Let's pick 5. You can repeat the same thing on all the other fields. Okay? And let's vary it once and then again. Once with parameter epsilon 1. First with parameter epsilon 2 and then with parameter epsilon 1. Okay? And then let's subtract from it what you get by doing things in the opposite order. Okay? So this is delta 1 of delta 2 phi. Now delta 2 phi is epsilon 2 psi. Epsilon 2 is the name of the parameter for delta 2. Okay. Now that I have done this, I need to vary psi with parameter delta 1. Okay. So this is epsilon 2 times the variation of psi, which is minus I sigma mu del mu phi epsilon 1 dagger. A phi or a phi star, I think it was a phi. Okay, so this is only the first term. So let's neglect this for now. This much is equal to this, which is equal to minus I epsilon 2 sigma mu epsilon 1 dagger del mu phi. Alright? Therefore, delta 1 delta 2 minus delta 2 delta 1 on phi.
We are again working into the results.
Thank you. Actually, yes, that's it. And actually, we'll find that the m terms won't change this commutator, whatever I'm going to give you as answer. Okay, so this is going to give me minus I. I have the first term epsilon 2 sigma mu epsilon 1 dagger, and now I'm going to get minus epsilon 1 sigma mu epsilon 2 dagger and times delta mu phi. Alright? Okay. Now hopefully we can convince ourselves that the dagger of this term is this term with the minus sign, so this whole thing is real. Okay, unlike just one of them. Okay, and this can be written as, I'm really not very concerned with signs right now, but the factors will be okay. It can be written as alpha I alpha mu t mu phi, with alpha mu the parameter being minus, or let's write it the other way, epsilon 1 sigma mu epsilon 2 dagger minus epsilon 2 sigma mu epsilon 1 dagger. Okay, so we've seen that the commutator of two supersymmetries on the scalar field is the derivative of the scalar field times some parameter. Okay, and I del mu, as you know, is p mu. So this also formally can be thought of as alpha mu p mu on phi. P mu is the momentum generator, which is represented as I del mu when it's a differential operator. Okay, and so we see that the algebra of supersymmetry is very roughly Q dagger equals P equals sigma mu P mu. But this is just a schematic representation of this, and I'll define Q very precisely, and we'll actually compute this anti-commutator, and we'll see what we should get. Okay, are there any questions up to this point? This is all reasonably clear? This is all very familiar? Does everybody know this already? Very well? No? Okay, good. Now we are going to use this as motivation to set up a structure where supersymmetry is manifest, and that structure is called superspace. So what we are going to do is think about the problem like this. Okay, we know that the right side has a geometric meaning. It's a translation in ordinary space-time. Okay, so p mu has a geometric meaning. The coordinates of flat space-time x mu just go to x mu plus alpha mu. Okay, or maybe I should have observed I in the word. This way, because it's alpha mu which has to be real if it has to be a translation of x mu. So I correct my earlier statement. I think this combination is real. Okay, so that's the geometric meaning of p mu. So does supersymmetry similarly have a geometric meaning in some space which we could call superspace? So could it be that this apparently accidental symmetry of the Lagrangian which we just worked out is due to some geometry in some space called superspace, which is obtained by enhancing physical space by some more coordinates or some extra dimensions, if you like. What would be nice if that's true is that then just by postulating that we are in that space, then we'll be able to rederive the supersymmetry algebra as a commutator of some geometric actions. We'll be able to find field theories on that space, and hopefully we'll find the most general field theory on that space with this symmetry. That's really the goal. Okay, because whatever I showed you, writing some free actions and showing that they have some symmetry, is no guide to how you get the most general theory. Okay, what interactions can you add, what can't you add? You could just keep struggling for a long time to do that. Much better if we geometrize this symmetry. So here's a natural guess. We extend x mu, which is flat space-time, Minkowski space-time, to the triple x mu, theta a, theta dagger, a dot, where theta are spinors. Okay, this is hopeful from many points of view. First of all, there's something spinorial about the symmetry. After all, the very parameter of the symmetry is a spinor epsilon a. So it's natural, just like the parameter of the translation is a vector. Okay, so it's natural to introduce coordinates of the same type as that spinor. In fact, once we are done with that, we might even like to guess that supersymmetry is implemented as theta a goes to theta a plus epsilon a, and theta a dot dagger goes to theta dagger a dot plus epsilon dagger a dot. The natural guess turns out to be wrong. Why is it wrong? Well, for this, let's recall what we know about the algebra of translations. Two different translations in any direction commute. Okay, so whenever there's no interesting algebra associated to translations, p mu comma p mu is 0. Okay, if we did this, we would find that the anti-commutator of two supersymmetries was 0, but it's not 0. We know that already in the field theory example we've looked at. So this is too naive. QQ dagger equals. Okay. So we choose something a little more complicated, and it's very easy to see. I mean, when I write it, it won't be obvious why I'm writing this, but you will see in a second that this is the right thing. First of all, we say, okay, theta A and theta dagger A dot do indeed translate as we liked, but that's not all. X also does something. That's the new ingredient. Now, there are not so many things X can do, because whatever it does has to carry a vector index, and it has to be proportional to an epsilon or an epsilon dagger. Okay, and that essentially gives you uniquely the following combination: minus I theta sigma mu epsilon dagger plus I epsilon sigma mu theta dagger. And it turns out that this is the correct set of transformations on superspace, which will reduce to the supersymmetries we know. You can see it in a microsecond, because let's look at X and let me make two transformations. So let me do delta 1, delta 2 minus delta 2, delta 1 on X mu. So you see what I've done. I've gone from a field, from the action of the symmetry on a field to the action on a coordinate, okay, which is more basic. And this now I can evaluate. So again, as usual, I'll do first delta 1, delta 2, and then I'll just subtract what I get from the other side. So it's delta 1 of delta 2x, which is this stuff with epsilon 2 in it. So minus I theta sigma mu epsilon 2 dagger plus I epsilon 2 sigma mu theta dagger. Now I do delta 1, and I notice that the only things left are thetas, and they are going to be translated. So I get minus I epsilon 1 sigma mu epsilon 2 dagger plus I epsilon 2 sigma mu epsilon 1 dagger, and this is great because I've already got the generator of translations that I showed you earlier. It's just epsilon 1 dagger sigma mu epsilon 2 minus the reverse. I might have, there's a thing between active and passive points of view, so I might have got my 1 and 2 mixed up, but it's of no consequence. If this is only delta 1, delta 2, but it follows that delta 1, delta 2 minus delta 2, delta 1 on X mu is with a factor of 2, 2I epsilon 2 sigma mu epsilon 1 dagger minus epsilon 1 sigma mu epsilon 2 dagger. So there is. So by inventing superspace, we've actually geometrized, we found a geometrical realization of the transformation whose commutator is a translation. Okay. If I do delta 1, delta 2 minus delta 2, delta 1 not on X but on theta, I just get 0 because theta just keeps shifting. So in fact, if I do a commutator on that, I get 0, which is correct. Because the translation finally is the translation in the bosonic part or the conventional space time part of the superspace. Yeah. Okay. Yes, that's correct. No, actually, theta naturally has, okay, good. X has dimension -1 in the same units in which a scalar field has dimension +1. Because the scalar field has dimension +1 in mass units, that's minus of length units. X has dimension -1, epsilon has dimension -half, theta has dimension -half. That makes these two equations consistent, so everything is consistent. It's a very tightly constrained system. Good. I still have a few minutes. Okay, I think we're making good progress. This might be repetition for many of you, but it will set again some conventions and so on for our future. So I might as well do it. Good. Now, we've invented superspace. Now, what do we do to make field theory on superspace? Okay. We simply invent a field which depends on all the coordinates of superspace. Now, that doesn't sound too good right away because the field, let me call it F, depends on X, theta, and theta dagger. But ordinary fields in field theory, including the examples we give, depend only on X and not on any extraneous coordinates. So how do we get rid of the extraneous dependence? And here we use the crucial fact that thetas are anti-commuting variables. variables. Maybe I didn't stress this enough even when I showed you the supersymmetry invariance of the Wess-Zumino model. But that invariance holds only if you assume that epsilon parameter is anti-commuting. Okay? In fact, everything makes sense only in that case because the boson varies into a fermion times an epsilon, and that combination is commuting if epsilon is anti-commuting. Likewise, the fermion varies into boson times epsilon, and both sides are anti-commuting because epsilon is anti-commuting. So that's important. And if epsilon is anti-commuting, theta has to be anti-commuting. Okay? So they are anti-commuting variables, and that literally means, let's look at them. There is a theta 1, there is a theta 2, there is a theta dagger 1 dot, which is the complex conjugate of that, and a theta dagger 2 dot. And these are all the thetas in our superspace. Okay. Any other one can only be something with a raised index, which is a linear combination. In fact, theta upper 1 is basically theta lower 2, and vice versa. So raising the indices just permutes these guys, but it doesn't do anything else. These are all that there are. Okay. Now, when we look at these components, then they satisfy some very obvious relations that theta 1, theta 2 is minus theta 2, theta 1, and likewise for any pair of these. These are not operators, they're just coordinates. So when they anti-commute, they just anti-commute. You just flip their order and it's a minus sign. Moreover, theta 1 is 0. And in the spirit of Wess and Bagger, now that I've written these two equations, you can write 75 more equations by putting all the thetas in it. Okay. Very important consequence is that no function can have more than 4 thetas, because the function on superspace can't depend on theta 1 squared because that's 0, or any of the other squared because they are all 0. So the maximum dependence it can have is that it can have a term theta 1 times theta 2 times theta 1 dot times theta 2 dot dagger, and that's it. So nothing, no more thetas you can multiply into that without making it 0. If I multiplied some fifth theta, wherever it was, I would anti-commute it till it hits its own friend in there and then gives me 0. Okay? That means that the Taylor expansion, we are used to the idea of a Taylor expansion of a function, let's say function of x about the point x equals 0. It's a power series which never terminates. But the Taylor expansion, I put it in quotes because it's actually much simpler than a Taylor expansion, about the point theta dagger equals 0 in superspace is finite. And here it is. I take f of x theta dagger. First of all, the first term in a Taylor expansion is when I put theta and theta dagger equals 0. So I'll give that term some name, f of x. Next, I look at the linear terms, and there will be a term involving theta. So I put the coefficient on its right. These are all conventions, and it's a function of x. And I understand that this is a spinor contraction with two undotted spinners, and the convention that this is up and this is down, which we already established. And then I put this root 2, which I hate with all my heart. But this is the root 2, which is why, if you noticed, I got some 2 somewhere in my anti-commutator and superspace. So between superspace and field, somehow there's a 2. I really hate this, but I didn't have time to get rid of it. Plus, I think in DGR's book, from where we are going to learn phenomenology, I think they keep this simple. So we live with it. Okay. So this is the term linear in theta. Now there should be a term linear in theta dagger. So we'll write that as root 2 theta dagger chi dagger of x. Notice that every term that's coming along is a function of x, because we put theta and theta dagger to 0. These are like the derivatives of this guy in theta dagger, and with the coefficient appropriate power. And you may wonder why I didn't put this to be the conjugate of this one. That's because the original F could be complex. In which case, what will happen is that F star will have chi dagger here and psi dagger here and chi. Okay, so they are independent. Okay, so let's keep going. The next term will be bilinear in thetas, and now we see that two component notation is coming in handy. If we have a term in two thetas, theta theta, then we can just write theta theta, understanding the contraction like this, times of field m of x, and another term theta dagger n of x. Okay. Now, what other terms can I have involving theta with theta? I can't have theta sigma mu theta, because sigma has a dotted and an undotted index. So I can't put a theta on either side. Okay. But I can have theta sigma mu theta dagger, which I'll have. I could have theta sigma mu nu theta. This I could imagine. But happily this is 0 by some symmetries. So I don't even have that. Sigma mu nu I could have had, because sigma mu nu has both undotted indices. So it allows me to contract theta with theta. Okay. And the general rule in this is that there are no higher things. Anything involving 3 sigmas has a linear dependency relation on things with lower sigmas. So there are so many terms. So let's write the next one as theta. So this I promised you, theta sigma mu theta dagger. This is allowed. The index contractions are standard, and the field which multiplies it must have an index mu to match that. Okay. Next. So this exhausts all the terms with 2 thetas. All possible terms I can make with 2 thetas. Next, terms with 3 thetas are quite simple, because they are really terms with 1 theta and terms with 2 theta made up of that. And moreover, if 2 thetas are undotted, then the third one has to be dotted, because one more theta multiplied on theta theta is 0. If you are wondering why theta theta itself isn't 0, can you guess? Sorry? What is that? 1 theta 2 components, yeah. Because of the raised and lower, this is really theta 1, theta 2 in components. Okay? And that's why this thing isn't 0, it should contain some shorthand. It's only in components you can be sure whether something has to be 0 or not. Okay? But since this is theta 1, theta 2, there can't be a theta 1 or a theta 2 here. So the next thing has to be theta dagger, and we'll multiply it by a spinor field, we'll call it lambda dagger of x. And then we have a term with the complex conjugate structure. For some reason these terms don't have any root 2. And finally, the last term has all the thetas once and for all. So by convention it's a half theta 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 dagger d of x. Okay, so we've just applied common sense to expand the most general superfield we can think of. It's actually not the most general, because we have not endowed it with any Lorentz indices, but we've allowed it to be complex. Okay, and we see that its first component for practical purposes looks like a complex scalar field. Okay, in fact I would actually much prefer already to call this phi. It's really when supersymmetry was invented that letters of the alphabet started to run out in this subject. But anyway, I think we should still keep the ones that we are familiar with. So that's phi. Now we can notice lots more things. Phi we should interpret as a commuting scalar field or classical fields. So this itself, although it's a superfield, it is commuting. Okay, that's possible because it may contain anti-commuting things, but then the coefficients of those will also be anti-commuting things. Here's an example. Theta is an anti-commuting coordinate, so we see that it must contain an anti-commuting field next to it, psi, which naturally we can think of as going to be a fermion field. Okay, so we see that some aspects of physics as we know it, field theory as we know it, are encoded in this very simple expansion. We have scalar field, we have a spinor field, we have a dotted spinor field, we have some more scalar fields, and finally here in the middle we have a vector field. Wonderful. Okay, and then we have some more spinor fields, and at the end we have another scalar field. And this is like that Pascal's triangle. Basically, you can see that there is one complex degree of freedom here. Then there are 4 to first order in theta, 6 to second order in theta, counting these 4 components of a mu plus these 2. Then 2 and 2, 4 here, and finally 1. So it's 1 for 6 for 1, which adds up to 16. So the field degrees of freedom (1 plus 4 plus 6 plus 4 plus 1 equals 16). Moreover, we see that this and this are all bosonic, and this are fermionic. Okay, because anti-commuting objects are fermionic, so they come to first order and third order in theta. Okay, therefore there's an equal number, 8 bosons, 8 fermions. We shouldn't be in too much of a hurry to think of these 8 bosons as 8 different particles. Okay, you can see that we counted a mu as 4 components, so these are really counting of off-shell degrees of freedom, that is before the physical conditions are imposed. Moreover, it's actually complex. And that's because the superfield is naturally complex. If we want to restrict it to real, we can. That we'll do next time. But we'll also find some other restrictions which are not compatible with being real. So we'll see all the possible restrictions on the superfield. Okay. So this has come along well. And now to close, I just want to notice that. Okay. So is this fine? Any questions on this? So to close, we'll ask the question, just as del mu or I del mu is the differential operator that generates translations, what differential operator in superspace generates supersymmetry? The answer is extremely simple. We know that one part of supersymmetry is the translation in thetas. So there must be. So if the operator that's going to generate supersymmetry is called QA, it's bound to be spinorial. There is bound to be a term I del A, where del A means del by del theta A. Now these derivatives are a nightmare because raising and lowering indices have potential minus signs. Okay, and for that I'll refer you to the book. So this theta A is really theta down with an epsilon. So this is the first step because this part will generate the translation in theta that we want. Okay, but it's clearly not enough because this has to also generate the shift in x by a theta dependent amount. Okay, what's the shift in x by a theta dependent amount? It must have a del mu to generate the shift. It must have a theta and it must have a sigma mu. So it's just a business of adding up, putting in all the indices, and we'll get our supersymmetry generator. So sigma mu, theta, del mu, and some factors of I. And so the standard definition is with a minus I in front and a plus I inside there. And what is the index structure? So A, B dot. Oops, I think this is theta dagger. B dot. It is. And Q A dot dagger needs to be worked out. So it's I B A dot. As I said, there are some subtleties about the definitions of these. They are all subtleties in signs, nothing else. And then you have I theta B sigma mu B A dot and then derivative. So here it is for once with all the indices put in, but once you get used to it, you can just say Q is I del plus sigma mu del mu theta dagger and so on. And you should check that this, if I act with this on X and on, so if I act with I epsilon Q plus epsilon bar Q bar, generates whatever we wrote earlier, X mu goes to theta. I'm not going to rewrite it. All the supersymmetric transformations in superspace that we wrote earlier are generated by these two differential operators in this combination epsilon Q plus epsilon dagger. Okay. And now that we have the generators, we can make a precise statement about what their algebra is, and we find that Q, when anti-commuted with another Q, is 0. That's because if you look at this has a del in theta, but this contains a theta dagger. So when I anti-commute them, this del is not going to see this theta dagger. Okay, because it doesn't differentiate theta dagger, it differentiates only theta. And there's nothing here depending on X, so this del doesn't differentiate anything, so the anti-commutator with itself has to be 0. But if I take QA with Q dagger B dot, then it's different, because this del differentiates this theta here, and this del A dot differentiates the theta dagger there. And both the contributions add with equal amount and same sign, so that we get 2 sigma mu A B dot, so del mu with an I somewhere. Absolutely, that's the answer. And as an operator, it is 2 sigma mu A B dot capital B. Okay, and then of course this equation has its dotted counterpart, Q dot also anti-commuting itself. So I urge you to carry out this calculation of anti-commuting QA with Q dagger A dot in this way, and seeing that you get this without the right mathematical signs. Okay.